So as we start thermodynamics, the first thing that we really need to do is talk about our definitions and these ideas of temperature and heat. There's a lot of confusion that students typically have about these two words and what these concepts mean. So let's try and clear that up as well as we can right up front. So for starters, there are two ways that we can transfer energy. One, we've talked about a lot, which is we can do work. So that's a transfer of energy due to some force acting through some displacement. The second way that energy can be transferred is due to temperature differences. So if I've got two objects and I put them in contact with each other and one of them's very hot and one of them's very cold, there will be a transfer of energy between those two objects because they sit at different temperatures. So heat is a transfer of energy due to temperature differences. So it will always proceed, that transfer of energy will always proceed from higher temperature to lower temperature. And the sign convention that we're going to use is Q is the symbol that we use for heat. Q is going to be positive when a system takes in energy as heat. Q is going to be negative when a system gives up energy as heat. So one of the things that I'm going to try and do as consistently as I can is never to just say the word heat. I'm instead going to try to always say the word energy transferred as heat. So let's say that here I have a system. Right? So here's some system. It's denoted by the purple boundary. So here's the boundary of my system. And that system sits inside some environment. So that's the green boundary here. So the relative temperature between my system and environment will tell me about the direction in which that energy is being transferred as heat, and then the sign that I need to use with Q. So let's say that my system is at a higher temperature than the environment. Well, I know that that tells me that energy is going to be transferred from the system to the environment. So Q, right, this transfer of energy as heat will go from the system to the environment. So if I'm thinking about the energy transferred as heat by the system, that's actually going to be negatively valued. If, on the other hand, the system is at a cooler temperature than the environment, so now the environment is at the higher temperature. So again, I know that energy is going to be transferred as heat from the environment to the system, which means now the system is taking in the energy, so the energy transferred as heat by the system is going to be positive. Last option, of course, is, well, what if these two, the system and the environment, have the same temperature? Well, then there's no net energy transfer between the system and the environment. So there, Q would be 0. So this is the situation where their energy is still being transferred, but the system is giving up as much energy to the environment as it's taking in from the environment, and this defines what we call thermal equilibrium. So thermal equilibrium is the point where my two objects, in this case my system and the environment, have reached the same temperature so that the net energy transfer between them is 0. So we've talked about, say, static equilibrium, where we said that the net force acting on the system was 0 and the net torque acting on the system was 0. Well, thermal equilibrium is just a statement that the net energy being transferred between your systems as heat is 0. Okay, so that's hopefully gives us a better idea about what we're talking about as heat. So heat is simply energy being transferred from one object to another, from a system to an environment, because of temperature differences. So now let's come back and talk about temperature. So what are some useful definitions for temperature? Well, the most basic one, as silly as it seems, is to say that temperature is what you measure with a thermometer. This is what's known as an operational definition, right? So what is the process that you do to measure something is basically telling you what its operational definition is. Well, if we want to measure temperature, we go grab a thermometer. And again, this seems a little bit silly, but there's actually some really useful information in here, because how is it that you take a temperature with a thermometer? Well, there are two things that are involved in that. One is that you have to put the thermometer in contact with the system. What this means is that there has to be a way for energy to flow into or out of your system. So when you would, when someone would take your temperature, right, when you were a child, and they'd put some thermometer under your tongue, well, putting the thermometer under your tongue was putting it in contact with you, the system. So the thermometer in the system had to be in contact, so there was a pathway for the energy to be transferred back and forth as heat. Now, there are a couple ways that we can think about materials, and basically it's whether they allow that energy transfer or not. So insulators don't like allowing the energy to be transferred into or out of the system as heat. They prevent thermodynamic interactions. Conductors, on the other hand, they permit thermal interactions. So conductors allow energy to be transferred back and forth as heat. They allow that energy transfer to go through. Insulators prevent that energy to be transferred back and forth. So we'll pay attention, right? It'll be important to think about when we're working our thermodynamics problems is, well, are we dealing with an insulator or not? So if our material is an insulator, then I know that it's going to inhibit transfers into or out of the system. The other thing that we had to do was you had to wait. So again, taking your temperature as a kid, you put the thermometer under your tongue, so there was contact between you and the thermometer, and then you waited. So there had to be a way for energy to flow, and then there had to be time for energy to flow. So both these things, again, as sort of basic as this definition sounds, it's actually giving us two really important ideas here, that in order for the energy to flow into or out of a system as heat, there needs to be contact, right? There has to be the ability for that energy to flow. So it can't flow across an insulator, it will flow across a conductor. And then you've got to wait. You've got to allow that energy transfer to happen. A second definition that we could use, and again, this is going back to what we talked about with thermal equilibrium, is that temperature is what's the same when two systems are in thermal equilibrium. So again, if you let two systems stay in contact long enough, and long enough basically just means that they've transferred their energy back and forth to the point where now they come to the same temperature, then they'll be in thermal equilibrium. So there are a set of 3 laws for thermodynamics, but they've been ordered kind of strangely because we ended up thinking about the one that logically needs to come first, but we didn't recognize it until after we'd sort of formulated the other 2. So it got kind of thrown out front and is known as the 0th law of thermodynamics. And basically what it says is that if you have 2 systems that are in thermal equilibrium, so if each of them are in thermal equilibrium with a third system, then they also have to be in thermal equilibrium with each other. So this is really just sort of a transitive property for thermodynamics. It basically says that if the thermometer and you are in thermal equilibrium, which means that the thermometer is registering your temperature, right? And you put that thermometer in contact with something else, and it also didn't change its temperature because they were in thermal equilibrium, then you and that something else are also in thermal equilibrium. So again, we can define temperature in terms of what we measure with a thermometer. We can define temperature in terms of what's going on with our process of thermal equilibrium. A third way that we could define temperature, and this is leading us towards where we'll go when we talk about the second law of thermodynamics, which deals with the concept of entropy. The temperature is a measure of the spontaneous tendency of a system to give up energy as heat. So again, we know that the hotter something is, the more likely it's going to be to give up that energy, because energy always flows from high temperature to low temperature. So it's going to flow from hot objects at high temperature to cold objects at lower temperatures. And so what temperature is another way to think of temperature is it's basically telling you what's the likelihood, what's the probability that this particular object will be the one to give up its energy as heat when you put it in contact with something else. So if I have a very hot object the odds are really good that that very hot object is going to be the one that gives up its energy when you put it in contact with some other system or put it into some new environment. Very cold objects, on the other hand, there's a very high likelihood that they're going to take in energy as heat. So temperature is telling you something about the likelihood of a system to either give up or take in its energy. And then the last one, and this sort of fundamentally will end up being the way that we kind of calculate things out, is that temperature is a measure of what's known as the thermal energy of a system. And the thermal energy of a system is usually some mix of the kinetic and potential energies of the particles that make up the system. So a couple systems that we could talk about is, so if we talked about a monatomic ideal gas. Well, monatomic ideal gas basically says that you're treating those gas particles as if they were little billiard balls pinging around, bouncing off of each other, bouncing off the walls of the container. And so what the temperature is measuring there is the average translational kinetic energy of all the particles. So you take all the 1/2 mv squareds and calculate an average of that for all the particles within your gas, and that's going to tell you about that's going to be measured by the temperature. If instead of a monatomic ideal gas, you started sticking those particles together, so you have diatomic or triatomic ideal gases. So again, now I'm taking 2 billiard balls, and let's say for a diatomic ideal gas, I'm taking those 2 billiard balls and connecting them with a stick. And so now I've got something that's got my gas particles on either end, but now some stick, or really some spring, that's connecting them. And so now that whole system can move, so it's got translational kinetic energy. I can stretch that spring back and forth so that those particles move back and forwards, away and towards each other, and then I can let the whole thing rotate around. So I just have more ways in which that system can move, and so I'm measuring all of those kinetic energies when I measure the temperature. If you want to think about solids, well, solids are atoms, molecules within some crystalline structure. And again, that crystalline structure basically says take all those atoms and connect them with springs. There will be some equilibrium point that they want to sit at. And so what temperature is measuring is basically how much those atoms bounce around away from that equilibrium point. So a very cold solid, those atoms are basically staying right around their equilibrium point. But if you get a solid that's nice and hot, then in fact what you're doing is you're getting those atoms so that they bounce around a lot, and they're putting a lot of stretching and compressing those springs as they bounce around, and that's what you're measuring. So here we're sort of, again, combining the kinetic energy of this vibration with the potential energy in sort of stretching and compressing those springs as they sit on that solid lattice. And so fundamentally at the atomic scale, that's really what temperature is measuring. It's measuring the motion and the potential energy of the particles that make up your system.